in a unique position in a certain way, because it was a part-time with us. And in 2.5 years, I was able to complete a very important project, which was understanding the impact of boulders and the morphological change due to the boulders around those, due to high flows in triggering hyporheic flows. And hyporheic flows, as Daniele will present us, is flows of stream water that moves into the sediment and that back in the streams. And in the last 20 years has been quite a hot topic in understanding not just the interaction between rivers and the surrounding environment, but really to understand how river works. And there's been an expansion between the concept of river that is just the surface water, with a new concept of river as a river corridors, which take into account both the water that flows on the surface, but also the water that moves into the subsurface. So it's my honor now to give the place to Taylor and present his work that he was completed recently with us.
Great, thanks Daniele, and I really appreciate the introduction and the kind words. All right, let me get my presentation here ready. All right, here we go. I'm gonna share my screen. All right, can everybody see that?
Yep.
Nods and everything, so we're good to go. All righty. All right, well, as Daniele mentioned, my name is Taylor Dudnak, and this is my master's thesis defense titled Effects of Boulders on Bed Morphology and Hyporheic Flow. Major professor, Dr. Daniele Tonina. My committee is Dr. Jeff Reeder, Dr. Elowen Yeager, and Stephen Hunt over at USGS. First off, I need to make sure I give proper acknowledgements to everybody involved with these efforts. First of all, Dr. Daniele Tonina, my major professor, he's been patient, persistent, and super dedicated to supporting me throughout my degree, and especially for welcoming me in with an awesome and great research opportunity at U of I in Boise. Made sure I was able to continue working for USGS as well as be a part-time student at U of I. Dr. Jeff Reeder, he's been extremely helpful and super guiding in all my research. We spent countless hours in the flume together, chatting about my research, talking about non-research related things, and overall just a really great person. So Jeff, I appreciate it. Elowen, you're awesome. You've been an extremely helpful person throughout everything and my experience at U of I. You've taught some awesome courses that gave great background knowledge to all my research. On Hale, you were great. I can't thank you enough for all your guidance through the publication process with my water resources research article. So I really appreciate all your feedback and support with that. All my CER graduate colleagues, Jenna, Brandon, Caitlin, Rain, Heidi, Andrea, Taryn, you all are awesome. And I couldn't thank you enough for just being a great support group throughout this whole process. Over at USGS, as many of you guys know, I'm also a part-time, I've been part-time and full-time throughout the summer, pathway student. And Stephen, you were great throughout the whole process of getting me started with my research, provided great background theory for mod flow, which I'll talk to you guys all about. Dr. Kyle Blash, he's the center director at the Idaho Water Science Center. I appreciate him for taking me on as a student contractor back in 2016 and then eventually allowing me to become a pathway student. Christian Schmidt, he's my direct supervisor at USGS. He's always asking me about how my research is going, and just been a very open ear for me. He knew when I was stressed with balancing work, life, school, all that, so I really appreciate him. Ryan Fossness, he's been great. He's been my mentor throughout everything, my whole career so far. And a colleague and also somebody that I can call my friend. So I really appreciate you, Ryan. Lauren Zinzer, she was also actually a U of I student of Elowin's, and she, if it wasn't for her, I probably wouldn't have known about the water resources program here in Boise. So I probably wouldn't be here without her giving me the helpful ear of this program. And finally, I'd like to thank all of you guys for calling in today. The support that I have from you all has been tremendous, and overall, I just really appreciate it. So let's get started here. First off, I want to paint kind of a vivid picture for you from an excerpt from an article published in EOS. It's a weekly magazine on earth science. So here it is. Beneath the rushing waters of any stream, there lies a peculiar zone of deposited sediment. Water from the stream, as well as groundwater, seeps into this nutrient-rich sediment, allowing a cornucopia of fish, plants, and other organisms to thrive and prosper. Furthermore, most of the chemical changes in a stream's ecosystem take place in this zone. Water flowing into this zone carries nutrients, pollutants, and dissolved oxygen. Water flowing back out carries transformed products and cooled water into the stream for other organisms to experience. So with that, I want to talk to you about this really exciting zone called the Hyporheic zone throughout my presentation. I'm going to provide general research questions that guided my research, followed by a few slides of background information regarding Hyporheic exchange and how Hyporheic exchange can be observed. Some previous research that helped guide my questions and background theory for Hyporheic exchange and modeling Hyporheic exchange. The study design is super important for how I was able to accomplish my results, as well as the conclusions and implications of everything involved with this research. So, slide. The research questions that helped guide my research were: what are the feedback mechanisms between Hyporheic exchange, streambed morphology, and in-stream structures? What geomorphic and hydraulic and hydrologic responses are expected to occur from macro-roughness elements? And how do properties of Hyporheic exchange change with different geomorphic conditions? So lots of words in there, and you probably noticed that I mentioned the term Hyporheic exchange or Hyporheic flow quite a few times. So if you don't already know or haven't really developed an idea of what Hyporheic is, I'll start off by providing a kind of a concise explanation of what that is. Simply put, the terms come from the Greek prefix hypo and rheos, which denotes under the flow. More specifically, Hyporheic exchange is the interaction and mixing of surface and shallow subsurface water through porous sediment in the stream bed. So you have gravels, sediment, sands, and boulders, where the water is basically moving through these interstitial spaces between the sediments, more or less. It's driven by any spatial and temporal variations in the channel characteristics, such as the flow hydraulics, pressure on the stream bed, sediment mobility and the volume of the sediment, as well as the hydraulic conductivity, which allows water to move through the sediment at various rates. For the purposes of my research, I investigated the Hyporheic exchange through a mobile stream bed, which is basically where sediments are able to move throughout the system. Hyporheic exchange is very important for fish and other biological processes. When water is effectively moving through the sediments, it moves as Hyporheic exchange and it's cooled. The water is rich in dissolved oxygen, which creates an aerobic environment or oxygen rich, and that can be useful for microorganisms to survive. As the water upwells back towards the surface, it's distributed through the sediment and back into the active channel where the water is moving downstream into the below basin. These upwelling zones are thought to be a preferred location for spawning salmon species, such as these guys right here. Overall, this is basically the extent for which Hyporheic exchange can occur. So we see various spatial extents that it will occur, and one example is around bends, river bends right here. So this red line kind of denotes what an intermeander scale of Hyporheic exchange can occur on. This is kind of a larger scale Hyporheic exchange. Other types of Hyporheic exchange that we see can be through gravel bars, such as right here, through riffles, or even through macro-roughness elements such as boulders, sand dunes, kind of like what we see right here in this bottom right picture. And even root wads, like trees that have come downstream and been stopped up in the middle of the river, the flow can basically downwell and come back up around those root wads, as well as other larger sediments like boulders and things like that. So it's a super interesting location where water is constantly moving, just as it is in the river channel. It's also doing the same thing below the river channel. So how do we actually observe hyporheic exchange? Well, there's a few different ways that this can be done. One possible way is through direct and physical measurements of the vertical head gradient in the river, which is basically a slope of water and how it can move between two different locations. This can be done by a series of nested piezometers like we see here in this left photo. They can be placed in the riverbed and observe the vertical head gradient, which is basically, like I said, upwelling and downwelling of hyporheic exchange. An alternative method for physically measuring hyporheic exchange is through a slug test, which is basically where you inject a tracer dye into the sediment, and that can be observed downstream through a change in concentration of that slug test. Another method of observing hyporheic exchange is numerically. And we can basically model what we would expect hyporheic exchange to look like in the river system. This is done through a series of complex mathematical equations and is commonly used for larger scale groundwater modeling through porous sediments and other various research types. So some previous work that I used to base my research on comes from a huge variety of research goals, kind of like what Daniele mentioned in his introduction. Sawyer et al. Back in 2011 investigated the effects of large channel spanning logs on hyporheic exchange. So logs that were jammed up in the river, kind of across the river and obstructing the overall flow. In this experiment, the logs blocked roughly 60% of the cross-sectional area of the flow. So the water was basically forced over, under, or around the sides of these boulders. It basically created high pressure gradients on the bed, which eventually drove the hyporheic exchange that they observed in their models. They concluded that a streambed that adjusted to the channel spanning logs the streambed had a negligible effect on the overall hyporheic exchange, and that using just a plain bed, a flat bed basically with no structures, would be a sufficient way to explain the overall hyporheic exchange. This was much different from my study because my boulders blocked a smaller percentage, roughly only 3% of the cross-sectional area, but the deposition and the erosion rates around my boulder were much larger relative to the boulder size compared to Sawyer et al.'s study. So something to consider going forward. Prishalak et al. Ran a series of numerical experiments to determine how the heterogeneity, or basically the sorting of the sediments in the stream bed, would affect hyporheic exchange. They concluded that the heterogeneity increases the flux between these different types of sediment that are in the stream bed by an order of magnitude relative to a situation where the stream bed is just homogeneous, where it's just basically one type of sediment that exists. So this basically drastically changed the shape of the residence time, or the time that it took for the water to go down and come back up. And it also decreased the median residence times. So something interesting as well to take note of. Ward et al., they used the results of numerical hyporheic exchanges, similar to what I did. Their simulations were based on various hydraulic conductivity treatments to demonstrate the usefulness of different restoration techniques. So they looked at the processes of nitrification, denitrification, respiration, and thermal buffering by putting these different structures in here, as you can see in this bottom right structure, or this bottom right figure. These pieces of material basically had different conductivity. So as you see here, the flow lines move towards this zone, whereas in this bottom figure, the flow lines moved away. So these different treatments in the river affected the overall movement of hyporheic exchange. These are only 3 examples of a huge list of hyporheic studies, like Daniele mentioned. My research fills a gap that fits kind of between the studies I just mentioned. As opposed to using macro-roughness structures that block a high percentage of flow, as Sawyer did, I mentioned my macro-roughness structures only were a small percentage of the overall cross-section. Similar to the Ward et al. Study, I modeled Hyporheic flow to examine the distribution of residence time of the flow paths going down and back up through the stream bed. Instead of determining how subsurface qualities, such as the different hydraulic conductivities, affect the Hyporheic exchange, I examined the effects of different bed surface conditions on Hyporheic exchange, which I'll talk about here in a minute. So different morphologies, basically, on the stream bed. So the overall experimental design was super important in how I was going to proceed with my experiments and my research. The first two steps of the experimental design would not have been possible without the help of Elwin and Angel. The data from their research, it was a 2017 Water Resources Research article that they published. The data came from their research. So I'll explain that here in a minute. The third step was subsurface flow modeling, which basically took the data from the previous step and modeled what the Hyporheic exchange would look like below the surface. The fourth step was a particle tracking and residence time distribution step that I used to examine basically the effects of Hyporheic exchange on these different bed conditions. So the first experimental design is kind of, I'm just going to give an overview of the work that Elwin and Angel did. Sorry, the data analysis that they used from this whole setup was super important for my research. They used the topography from an initial bed condition and a final bed condition. So you'll see that here in the second figure here and the third figure here. Their study used data to examine the grain size variability in low relative submergence regimes. And so let me describe the three conditions that I use in my analysis, but I'm going to skip the first. So the second here, this is the initial bed condition, and it was characterized as a relatively flat stream bed composed of medium-sized cobbles and pebbles, gravels, along with multiple simulated boulders. So you'll see some circles here, and those are actually the boulders. I'll show you a photo on the next slide of what they actually look like in the flume. Nonetheless, these boulders had a diameter of about 15 centimeters and they protruded from the stream bed. You'll see that there's more boulders here upstream and downstream, but this zone right here is the zone that I used to study Hyporheic exchange. This was the reason for these boulders was kind of to allow the flow on the surface and the subsurface in the models to fully develop before I analyzed the data in this study section. So using a high accuracy sub-millimeter accuracy laser scanner, they basically scanned the stream bed in this initial condition, and this was before moving water through the system. So they placed these boulders throughout the reach and scanned the topography of the stream bed. In the final condition here, they moved water through the flume, and this flume is located here in Boise, so we're really fortunate to have this at our disposal. The flow in the flume or river was 0.06 cubic meters per second, and they used various slopes in their study, but for my sake, I used the 2.15% slope for my study. They moved the water through the stream bed through the flume until equilibrium conditions existed, and this is essentially when the upstream sediment supply was equal to the transport capacity, which was calculated in the system. The transport capacity was roughly 0.06 kilograms per second of sediment moving through. Another equilibrium condition that had to be met was when the bed and the surface water slopes were constant. The reach average velocity also needed to be consistent, and they measured that using an acoustic Doppler velocimeter, which measured the flow essentially. The grain size distribution exiting the flume also had to equal the upstream sediment supply. So once all of these conditions were met, they called it equilibrium. Shut the water off and then scanned the bed topography again. And this is what I'm calling the final bed scenario. And that's something to keep in mind throughout this whole talk. After that, what I did was created a DEM of difference. And this basically is the final bed topography here minus the initial. And what it does is it essentially shows you areas where deposition occurred. So these darker blue areas along the side are areas where sediment was deposited. Upstream of these boulders, sediment was deposited. Conversely, downstream of the boulders, erosion existed. And this is all basically a function of the hydraulics that are imposed by the boulders in the system. Overall, there was some sediment that accumulated in the system, so that's something also to keep in mind. And then I'm going to jump back to this first scenario. What happened here was this is what I'm calling original plane bed. And what they did was they digitally removed the boulders from the initial condition and essentially called it flat. So you don't see these boulders that existed in this initial scenario, or this original plane bed scenario. So here we have 3 different bed scenarios, and that's what I'm going to use to model the subsurface hyporheic exchange. As I mentioned, I was going to show you some photos of what the flume looked like. These are the boulders that existed in the flume and the water moving through the system upstream to downstream. The next very important step in obtaining what I needed for my model was a pressure distribution on the stream bed. This was very important for me to model the subsurface flow, and these data also came from Angel and Elwin, as I mentioned. They used a large eddy simulation model coupled with a volume of fluid model, which is basically calculating the fluid dynamics in the system and how water's moving through the flume. The equations were solved using software called OpenFOAM. Details of how and why these models were used can be found in their journal article published in 2017. But overall, as a summary, the large eddy simulation is basically a model that's used to solve the highly sophisticated partial differential equations called the Navier-Stokes equations. And they basically describe the motion of viscous fluids and describe the conservation of mass and momentum of Newtonian fluids in a river. It was suitable for their application because it allowed for the consideration of local and macro-roughness elements such as the boulders. And the cell resolution was super fine at 0.5 millimeters. So they were able to describe what was going on in this system at very, very fine detail. The volume of fluid model had to be coupled with the LES model because the water depth was constantly changing around the boulders, especially because there was plunging flow as the water moved over the top of the boulders. Basically what it did was track the water surface elevation throughout the model period. So the flume, once again, super important for the sake of my study and Elwin and Angel's study. These photos here on the right depict the velocities near these boulders. So the red is higher velocities, and the flow, just a note, is moving from back here forward. So imagine a boulder right here, as it is here. The water's moving over the boulder and accelerating, kind of like what you see over in most rivers, actually. Think about driving along Highway 55 and you see the Payette River, lots of turbulence going on. The water's plunging over these rocks and creating high velocity zones. And then in the wake of the boulder, right there, right at the stream bed interface, there's turbulence going on and water's actually slowing down. It's the wake of the boulder, basically. So these surface flow characteristics really influence what's happening on the stream bed, the pressure distribution. So I'm gonna move forward here. The next step was to model what's going on in the subsurface. So this is the guts of my research here. After using the fluid flow modeling to determine how water is moving above the bed surface with the 3 different bed conditions, the next step was to look at what was happening below the surface or within the stream bed. So to do this, what I used was a software called GMS by Aquaveo. It's the groundwater modeling system. And what they have in that software is a widely accepted model called ModFlow, which was developed by the U.S. Geological Survey. And super interesting program that can be used on a variety of scales, but mostly it's used for large groundwater systems. So Conversely, I'm not using it for a large groundwater system. I use it for a very small groundwater system, or the hyporheic zone. Skipping forward, what's happening in mod flow is it's a finite difference method that calculates the groundwater equations through a cell. Mass moving in equals mass out, or mass in minus mass out equals some change in storage. So it's calculated via this series of equations. And so this is one cell. And if you would imagine, hard to imagine actually, my model used 16.2 million cells. So these equations were being calculated via mod flow in GMS for 16.2 million cells. Pretty hard to fathom, pretty hard to even understand how that can happen, but it does, and it's awesome in my opinion. The boundary conditions are super important for setting up the groundwater model. It basically describes what's happening at the upstream and downstream end of the model. And for me, this was the upstream face, so you can't quite see it in this image, but orange there, and then up on the surface, which is where the bed is, and then the walls of my model and the bottom of the model. So for my boundary conditions, I assigned these upstream and downstream and the top surfaces as a constant head, a specified head value, a pressure value that I knew from the surface water modeling portion. The bottom and the walls of the model were considered a no-flow boundary. So water could not move in my model through these surfaces, basically. And that basically, with all of those boundary conditions set, determined what the overall gradient through the system was and moved water through groundwater, through the ground, through the subsurface. Two other super important model parameters for this groundwater model was the hydraulic conductivity and the porosity of the sediment. The hydraulic conductivity was 0.01 centimeters per second. So it basically allowed water to move at a rate of 0.01 centimeters per second. This basically describes the intrinsic property of the sediment and how easily water can flow through it. The porosity describes how much water the pores between the sediments can contain. So this is an important consideration with all of these model parameters for modeling. And regarding the presence of boulders in each of my bed conditions, they affect how the subsurface flow is moving. Boulder surfaces, on the bed here were assigned a hydraulic conductivity value of 0 because, well, water can't move through the boulders, and we wanted to use this to force the hyporheic exchange to occur through the bed. This is the result of the subsurface water flow modeling. So the original plane bed, the initial plane bed, and the final plane bed. And the scale here, these darker blue values represent higher pressure values, and these lighter values are lower pressure values. So overall, high to low, that's what drives the groundwater flow. But there's also things happening near the boulders that are important to consider, which I'll describe here later. There's low pressure on the top of these boulder tops, and in my opinion, that's the result of the plunging flow dropping over the boulders. And all these pressure values on the surface were originally assigned, and then the model itself would calculate what the pressure values were below. So if you look closely, you can kind of see there's different shapes in the subsurface of these contours, and that's basically describing what's happening at the pressure level in the subsurface. Higher pressure values upstream of the boulders occurred upstream, like I said, upstream of the boulders, and then lower pressure downstream. And this is what drove the near boulder hyporheic exchange. And one other reason for the downstream lower pressure values is the higher velocities in the wake of the boulder created the low pressure zones, which is why the hyporheic exchange, which I'll show, moved upstream to downstream around these boulders. Another important point to think about is the fact that the bed is also changing from this second scenario to this third scenario because of the fact that there's sediment transport occurring. So erosion upstream or deposition upstream and erosion downstream, that's also driving the hyporheic exchange within the model. So as I mentioned, I investigated the results for these 3 different bed scenarios. What I also did was investigated the results at different spatial resolutions. So I looked at it from a large reach scale, or in my case, the study area, from just upstream of the boulder 1 to just downstream of boulder 6. That was the reach scale that I looked at. The second scale that I looked at was the near boulder scale. And what I did here was kind of an iterative process of examining the hyporheic exchange around the boulder. And I'll describe how that iterative process occurred. But basically it was 15 centimeters upstream, or the boulder diameter, 15 centimeters downstream, and then half a boulder diameter, or the radius, in the cross-stream direction. The next step was a means of describing what was actually happening to the hyporheic exchange. So we had a pressure field, but how was that influencing how the water was moving through the subsurface? ModPath is a software that is coupled with ModFlow, and what it's basically doing is tracking particles of water as it moves through the subsystem. So it tells you at a point in space, X, Y, Z, and time, where that particle exists. So I was able to track a single particle through space and time and determine the spatial characteristics of hyporheic exchange, basically. ModPath is a post-processing tracking program, and it's also in GMS, which made it really convenient. So I basically had to seed or drop particles into the subsurface and track them as they moved. Based on observations of Tonina and Buffington, the thickness of an armor layer, or an armor layer is basically a coarse layer of sediment above a layer of finer sediments, but the armor layer is essentially what they've observed to be 2 times the median grain size of the bed. So for my case, I seeded particles approximately 2.5 centimeters below the stream bed surface, because the median diameter of the sediments was about 10 centimeters, so 2 times 10 is 20, and I went just below that surface, so 2.5 centimeters. Due to the pressure distribution throughout the model domain, some particles were observed to upwell immediately upstream of the boulders. So what I did was I excluded those from my analysis and only included the particles that were downwelling upstream or anywhere near the on the bed. I also excluded particles that exited the downstream boundary condition. That was only 2% of the overall particles, so pretty negligible for that sake. But this figure down here represents kind of the conceptual understanding of what hyporheic exchange does throughout my 3 bed scenarios. The original plain bed, you see some shallow hyporheic exchange happening, as well as some more regional hyporheic exchange. As you add boulders, what I hypothesized is that the hyporheic exchange would downwell farther into the bed. There'd be fewer shallow hyporheic exchange flow lines, but they would downwell farther. And I wasn't quite sure what the velocities and that kind of thing would happen to what would happen with the hyporheic exchange, basically. But as sediment transport happens, you see some deposition upstream of boulders, and then these holes that are dug out, erosion downstream of the boulders. And what I hypothesized was that the hyporheic exchange would in fact increase near those boulders. And I would soon find out exactly how that would be affected by those boulders and the change in topography as a result of the presence of those boulders. So the results of my my analysis, like I mentioned, was from a reach scale standpoint and a boulder scale standpoint. I wanted to look at the spatial characteristics, or how broadly the hyporheic exchange moved across the stream bed and under the stream bed, as well as the residence time, or the time that hyporheic exchange existed in the subsurface. As I also mentioned, there's the three bed topographies, so that was important to consider for how exactly bed morphology was going to affect hyporheic exchange. Let me get into the results here. So on the reach scale, these 3 figures summarize how residence time of hyporheic exchange changed through the morphological evolution of the stream bed. So the original plain bed, on the left side of each of these figures, exhibits limited topographical variability because it was flat. There was no boulders. the pressure distribution was fairly uniform across the stream bed. And this resulted in hyporheic exchange times that were longer on average and more variable. We see that they're longer here in this mean time, residence time, and then they were more variable based on the standard deviation of the residence times. As the variability in topography and surface pressure increased through the presence of boulders and bed morphology, the standard deviation in residence times increased in the final bed scenario from the initial bed scenario. I thought this was a result of the deposition and erosion upstream of the boulders due to the adjustments on the stream bed surface in the final bed scenario from deposition and erosion. The downwelling flux, or the rate at which the hyporheic exchange downwelled into the surface increased. So I'll talk about that here in a second in a couple slides. The mean and median residence times also decreased as a result of the bed morphology. The mean residence time was always greater. So right here we see about 3.5 was greater than the median, 0.8-ish. This gave me some insight as to the distribution of the residence time. So whenever the mean and median don't equal each other, that gives you insight as to what the shape of the distribution of residence times are. And so since the mean residence time was greater than the median, I figured that there was some sort of skewness in my distribution, and I wanted to investigate further what that amount of skewness was. So with those residence time statistics that I just described, the indicators gave you ideas as to the shape of the distribution. So here's a cumulative distribution function of the residence times, as well as a plot that relates the observed probability of my residence times to a log normal probability. So specifically for each bed scenario, the mean was, like I said, always greater than the median, and there was some amount of skewness. So to determine how much these distributions were skewed, what I did was performed a goodness of fit test. Specifically, I used the Kolmogorov-Smirnov test, or the KS test, which basically is used to compare some empirical distribution to a reference distribution. So my reference distributions for this case were a normal distribution and a log normal distribution. And the null hypothesis of this test basically says that the empirical distribution, or the values that you observe, come from the same distribution as the reference distribution. I had evidence that had suggested the residence times were not normally distributed because the mean and the median were not the same. And so despite how each of these, the initial, plane, and final residence time distributions were a little bit different, I compared them to the log normal distribution to determine how close they followed to that distribution. The results of that KS test showed that, well, the critical value, or the value at which 95% confidence you could say that they match, was 0.0068. This test indicated that the log normal distribution is a very good approximation of the residence time for the initial plane bed, so the red. However, it was only a rough approximation of the original and final bed scenarios, because the test statistics were slightly greater than the critical value, or the value at which we could say 95% confident that they were the same. These results confirmed our initial observation that the distribution was not normally distributed, and that there was some amount of skewness. So that's super important to carry forward, because we can say that at least for the initial bed scenario, the distribution of residence time is log normally distributed. And this can give us insight as to different systems that residence time will be log normally distributed when you're investigating hyporheic exchange. Moving forward here, the reach scale, spatial characteristics are also important to look at, as well as the boulder scale, which I'll talk about here in a second as well. The morphological changes on the stream bed alter the residence time, which I showed you, but also the spatial characteristics. Draw your eyes to the center column here. And for simplicity, these lines only show a small fraction of the overall hyporheic exchange that happens in the system. If I showed you all of them, you wouldn't be able to make any sense of this. But nonetheless, the original plane bed, pretty chaotic hyporheic exchange happening. And then you move to the initial, where the boulders are present. You see some lines that are moving down, downwelling, and then coming back up, downwelling, coming back up. in and around the boulders. And then once you move into the final bed scenario, you see some more chaotic and not very deterministic patterns happening in this system. So just something to keep in mind about hyporheic exchange. It's always moving in a chaotic fashion, but generally it's moving with the gradient of the pressure. The top left plot shows you kind of an observation that I observed for this reach scale. So the mean downwelling flux increased as you made the bed more complex. Lower when it was a plain bed, and then higher when you include the bed morphology and the presence of the boulders. Hyporheic discharge also increased noticeably. So from the mean downwelling, the flux right here, the flux increased 18% from the original plain bed right here to the initial plain bed. But then when you include the boulders and the induced morphological changes going to the final, it actually increased by like 80%. And the median residence time decreased, which I showed you a couple slides ago, from the plain bed scenario. This suggested a couple effects of boulders and bed morphology that affect hyporheic flow more than we originally hypothesized. So this explains why the mean residence time also decreased as the bed underwent changes. The erosion and the deposition upstream and downstream of the boulders play a big role in how hyporheic exchange is moving through the bed subsurface. Majority of the flow was shallow, but you also have to look at the deeper hyporheic exchange flow lines. Those deeper hyporheic exchange flow lines made up the tails of the residence time distribution. That's why it was skewed. There was fewer, deeper, longer residence time flow lines, and there was greater, shallow, shorter residence time distribution flow lines near the boulders. Hyporheic volume, this basically describes the volume between the surface of the bed and the maximum depth of the flow line. So what I did was I looked at all these different flow lines and calculated the volume between the deepest point on that flow line and the surface. So as you add complexity to the bed and morphological changes, the total amount of water in the subsurface increased from a system that had no morphological features, no macro-roughness features. You'll also see that the depth of the hyporheic exchange also greatly increased as you added morphological complexities to the system. So going back to my other scale of analysis, instead of the reach scale, to talk about the boulder scale. So you'll notice a couple properties here in these figures. Well, boulder 2 always has a spike, and I attributed that to the fact that boulder 2 actually had the most amount of morphological changes, more deposition and upstream and erosion downstream than any of the other boulders. So the mean and median residence times were much higher here because it was forcing the hyporheic exchange to happen on a steeper gradient. These observations were also log normally distributed, just as they were on the reach scale, which, as we can see here, they follow all a similar trend. Boulder 1 and 2, these gray and yellow lines here, they are a little bit closer than the rest of the boulders, but I attributed that to the fact that, well, both of these two boulders experienced either the greatest amount of morphological changes, boulder 2, or the least amount, boulder 1. As I had just stated, the KS test showed that they were all a good, log normal distribution was a good approximation, not the best observation, but a good observation of a good representation of the distribution of residence times. So let me skip ahead to the boulder scale spatial characteristics here. So what's happening at a boulder scale, this is exactly what hyporheic exchange looks like. So you have the presence of a boulder, water cannot move through the boulder, so it has to move around the boulder, whether it's above in the stream flow or down in the subsurface as hyporheic exchange. We have initial bed conditions here, and then the final bed conditions after morphological changes. I talked about how I seeded the particles 2.5 centimeters below the surface. What I had to do was the iterative process that I mentioned earlier, and this was basically seeding the particles in all these downwelling locations of the bed around the boulder. So 15 centimeters upstream, 15 centimeters downstream, and then half a boulder width across. And so each of these flow lines represents a location where the Hyporheic immediately downwelled. So places like around here, you would say that, well, that's within a half a boulder width near the boulder. Well, those flow lines actually upwelled immediately. So I only looked at these downwelling locations. And here, the Hyporheic is downwelling, and then it comes back up on the sides of the boulder, right down here. This is a plan view, so looking down on the boulder, and this is a cross-sectional view. Downstream of the boulder, interesting things also happen. The particles were seated right around here, and they actually moved upstream in the subsurface. So they downwelled and then came back up towards the boulder. Same goes for the final scenario, but you'll notice a couple differences here. So in the final scenario, the flow lines actually went deeper as compared to the initial. And they had shorter residence times because the downwelling flux had increased in the final scenario. That's why this blue line here represents downwelling fluxes that are greater than the initial condition. Hyporheic discharge also increased, like I mentioned. The Hyporheic depths, they were generally always higher for the final bed condition, but noticeably it was also lower in some scenarios like boulder 4, and that's just a function of the morphological conditions that are happening near the boulder. So overall, the morphology around a boulder after you place a boulder in the stream bed plays a huge role in exactly how Hyporheic exchange is moving through the subsurface. The bed adjustments imposed by the flow above and below the boulders decreased the mean residence time by about 7% and the median residence time by 25%. The standard deviation increased on average across, if you were to average all of these boulders together and the effects of the morphological conditions from the boulders, the standard deviation increased on average by about 23%. So the flux, the residence times were more erratic, basically. The Hyporheic discharge also increased by about 9%, and the discharge, or the downwelling flux was increased by about 9%, and the Hyporheic discharge by about 28%, respectively. So with all these data and all the figures that I just threw at you, you might be wondering, well, who cares? What are the consequences of these results? A side note, I actually just changed the title of this slide because conversation that I had with Ryan, my coworker, I was trying to figure out what level of detail to include in this presentation, and he donned this little phrase on me. So as you'd say, don't bore us, get to the chorus, Ryan. So what are the implications of the work, basically? I'd like to tie this all together into something that we can relate to, and that's Idaho. All of us, from what I see, all live here in Idaho, and one thing that we all have in common is the fact that there's rivers around us. And this left photo here actually took at the middle fork of the Payette. Right photo is the middle fork of the Boise. Despite being totally different rivers, the one thing that they do have in common is that they're both the headwaters of their respective rivers. They're composed of gravelly bottoms with macro-roughness structures. So you see these large boulders in the middle of the river, these large boulders on the bottom of the river, and they're scattered about. Just as the boulders were in my research. So many mountainous streams such as these have similar morphologies, and large woody, whether it's large woody debris, step pool sequences, or even these large boulders. Therefore, my framework that I used in my research can be used to describe systems such as these, and it's very applicable to those types of rivers. I've demonstrated the importance of bed form scale geomorphic responses and the processes that occurred with those responses, whether it's the surface flows or the subsurface flows. Since stream beds and headwater streams are constantly adjusting to sediment inputs, hydrological inputs, whether it's increasing flow or sediment moving down through the river, as well as the presence of these macro-roughness structures, the local and reach scale variations in hydraulic head distributions are always changing, and they must be considered when you're calculating the amount of Hyporheic exchange that happens in a system. So analyses that don't consider these processes, they might be completely quantifying the Hyporheic exchange wrong. For example, I showed that on a reach scale, the median residence time increased by 15% from the plain bed condition. But after the stream bed fully adjusted to the morphological inputs, the residence time decreased by 20% from the plain bed. So if you're looking at a system that hasn't fully adjusted to the morphological conditions, your questions as to how hyperheic is exchanging could be completely wrong, and an oversight that could be detrimental to the findings of your hyporheic research. If stream restoration practitioners wanted to increase the residence time or just overall change the residence time of hyporheic flow by placing low conductivity structures such as boulders in the system, they must incorporate some sort of geomorphological aspect into their modeling efforts so that they can accurately depict what's actually happening on a hyporheic exchange rate and residence time. So the results from my study can be capitalized when the goal of the restoration efforts are to increase the surface and subsurface flow interactions, hyporheic exchange, provide some sort of habitat heterogeneity by adding complex structures into the system that will change the hydraulic properties around the boulders, or even recruit spawning fishes to live near these rivers, near these boulders. They tend to hide behind the boulders where there's some sort of hydraulic refugia. And salmon have actually been known to seek streambed sediments where hyporheic exchange is upwelling. That was found by a study by Baxter and Howard in 2000. So with the encroachment of developments happening near mountainous streams, whether it's homes and cabins such as the Middle Fork of the Payette, all these sediment inputs are changing, and people are starting to live near these rivers. Well, the natural connectivity of the rivers and their surrounding riparian zones are constantly changing. So ensuring the river maintains some sort of connectivity with the shallow subsurface is super important through means such as hyporheic exchange. That's a larger reason for why there's connectivity between the surface and subsurface flows. One reason that the hyporheic exchange acts as a pathway for filtering water is because the water's downwelling and it's cooling down, and then nutrients are being transferred between the surface and the subsurface, and the subsurface is where all these little bugs, macroinvertebrates, microorganisms exist, and they need to flourish. So the cold water, the high oxygenated water is allowing them to survive. Other things such as rooted vegetation in the river require some sort of nutrient uptake, and if nutrients aren't coming into the root systems, then how are they supposed to survive? So this is another implication of the work that I found. So fully understanding the effects that various factors have on hyporheic exchange is very important. Some limitations of my study include the fact that, well, the study started in the flume. So this is obviously a simplified version of a mountain river, and it captured, I mean, for the most part, it captured most of the fundamental processes that occurred in a river, including a feedback of water, sediment transport, and the macro-roughness structures that are changing the flow properties. Allowing the bed surface to freely adjust to the final bed, in the final bed condition, was also a good representation of what a geomorphic response might look like in a natural system. So we didn't want to limit the model in that respect. Overall, I presented here a proof of concept based only on one case of how the geomorphic properties can change. Obviously, the river is always moving and it can take different shapes and forms. So if we look at a meandering river, the results might vary a little bit, but I would still predict that the residence times would still be log normally distributed for this type of system. Another overall limitation of this model was the fact that I assumed that the subsurface sediments were homogeneously distributed rather than heterogeneously distributed. So if there's different sediment types where the conductivity is different, it might alter how the residence time distribution is distributed. But in nature, stream beds are generally heterogeneous. So if we take that into consideration in different models, we might be able to better predict the residence time distributions. So overall, to conclude this long-winded presentation, I just want to leave you with a summary of the findings of my research. My modeling of hyporheic flow through the subsurface of these three different gravel-bedded conditions are typical in mountainous streams. I was able to visualize and quantify the feedback between macro-roughness structures and morphological changes to the bed surface, alongside with the expected changes to the various Hyporheic exchange characteristics. Results from my study depended on multiple instream processes, the first being flow hydraulics. With the presence of boulders on the stream bed, more turbulent flow existed in and around the boulders, where the plunging flow occurred and localized velocities increased along the longitudinal profile of the boulder. Small eddies in the wake of the boulders also were noticed within the model, and these hydraulic properties that altered the sediment is what ultimately affected the Hyporheic exchange as much as it did. My results showed that the morphological changes originating and developing from the presence of the instream macro-roughness elements had a greater effect on the Hyporheic flow than just the presence of the boulders. Areas of the deposition and erosion developed in each scenario were generally deterministic of the gradient, the hydraulic head distribution around the boulders, and the overall flow direction of the Hyporheic flow. The induced morphological changes in turn increased the mean downwelling flux by nearly 50% and decreased the mean residence time by about 10%. Also worth noting is the fact that the total Hyporheic exchange increased by nearly 60% for the entire reach after the bed finally adjusted to the imposed conditions from the boulders. The geomorphic response to the boulders was not as strong as what we saw in the reach scale, but overall the mean downwelling flux near the boulders increased by 9%, and the median residence time decreased by about 25%. But more notably, the total Hyporheic exchange increased by about 28%. And overall, the log normal distribution would be a good approximation for the residence time distribution. So overall, the results of my study suggest that the geomorphic processes must be really considered when modeling Hyporheic exchange with macro-roughness elements. And also, this is my the research article that we published with the help of Daniele and Jeff and Angel. So if you want to read more into my research, you can read this journal article here. And with that, I'd like to open it up to any questions. Just make sure you unmute yourself whenever you do have a question.
Taylor, yeah, very nice. The mod flow model assumes kind of a laminar groundwater flow, I believe. Any comments on if there might be some turbulence effects, especially near the surface where the turbulent water is plunging into the bed?
Yeah, so as I mentioned, the turbulence that's happening around the boulder specifically, the plunging flow, these higher velocity areas that occur over the top of the boulders, once the flow moved over the top of those boulders, it created a zone in the wake of the boulders, behind the boulders, where the velocities were much slower. So that turbulence itself, the low velocity areas coincided with low pressure areas below the boulder. And that low pressure area is what drove the gradient across the boulder. So the higher pressure zones upstream of the boulder on the bed surface drove the Hyporheic exchange under the boulders or laterally cross stream around the boulders. And so in my opinion, the turbulence associated on the surface, such as the plunging flow, is what altered the Hyporheic exchange properties underneath the boulder.
Yeah, so clearly important in the water column, as you just discussed.
Absolutely.
Yeah, and my question is, are we perhaps missing something within the bed because the mod flow treats it as laminar flow once it gets into the bed?
Yeah, that's a really good point. So I think one way that we can incorporate the turbulence that might exist, since I used a kind of a homogeneous system in the subsurface, I think if we included various types of substrates that have different hydraulic conductivities, we might be able to see that turbulence in the groundwater a little bit better, because that's ultimately what's changing the flow rates in the subsurface. So I think that's a good point. If we included different hydraulic conductivities, then I'd be able to quantify how the residence time is changing due to the turbulence or the chaos of the flow in the subsurface.
Thank you.
Yep, thanks.
Hey, Taylor, I've got a follow-on to that question that maybe would help you sort of get a notion of potential turbulence. And maybe I'm just not remembering very well, but did you speak at all about the estimated velocities, subsurface velocities, and how they changed as the water progressed on its path from its initial downwelling to its upwelling?
I didn't explicitly describe that. Are you finished with your question? Sorry.
Yeah, that's fine.
Yeah. So initially, the downwelling fluxes that I described in my presentation are the initial downwelling fluxes. So it's the initial velocity at which the water's downwelling. So I didn't necessarily describe how that velocity is changing through the downwelling, through the portion of which the residence time or which the particles exist. But from my understanding, the velocities slow down as they go deeper into the subsurface, and as they come back up towards the surface, they speed up again. So that's a portion of the Hyporheic exchange that I didn't necessarily quantify, but just the downwelling portion.
Okay. Yeah, and I think I was asking that question, you might be able to, so mod flow solves the groundwater flow equation, which does assume there's no turbulent flow. So you may be able to sort of hack your way around that as you suggested, but I think what Ralph was questioning was, to what extent maybe would that assumption be false if there was some sort of turbulent flow in the near subsurface? And you could potentially look at velocities along with your estimated porosity to sort of, to see to what extent you might expect that to take place.
Sure. So in my output from ModPath, I track for each location that particle existed, and I could calculate that velocity between, I guess, each observation within that ModPath. So that would also be a good way to determine what the effect of turbulence is on the residence times. Thanks, Stephen.
Hey, Taylor, nice job. Super interesting research. I've got a question for you that's kind of on like the other side of things. Okay. It seems like there's a lot of applications I can imagine where you'd want to increase Hyporheic flow to facilitate restoration initiatives, but I can also think of a scenario in which maybe you have like high metals concentrations in your sediments, and really what you want to do is limit Hyporheic exchange in order to limit the amount of metals that would be pulled up into suspension and into the stream. And so from your research, what sort of design elements might you suggest to limit Hyporheic exchange?
So if we're trying to limit how much water is actually going into the subsurface, then I think, well, first of all, adding any complexities to the surface of the bed itself, that's one thing. But it's hard to remove any irregularities on the bed surface in general. But I think if we have some sort of sediments that do allow for what is Hyporheic exchange, I guess, to stay in the subsurface longer, then that would be one way too. Even though we aren't necessarily limiting the Hyporheic exchange, we're increasing the time that the Hyporheic exists in the subsurface. So if we're trying to kind of store away those metals that are coming down the river in the subsurface, that'd be one way to do it, is to put in different subsurface sediment types that basically change the hydraulic conductivity of the bed. So, but your question is basically, how do you just overall limit the Hyporheic exchange in general? To me, I think that would be more of a surface water question, because you'd have to consider altering the flow, I think, because the flow is what's ultimately altering the surface pressure on the bed, which drives the pressure gradients for Hyporheic exchange. So if there's less turbulence in the river, maybe that's one way to limit the Hyporheic exchange through the subsurface. So creating more of a laminar flow condition as opposed to turbulence. I think that'd be a good way to do that.
Cool, thanks, Taylor.
Yep, thanks, Lauren. Tyler, I think you had a question.
Yeah, I've got Actually, kind of two questions. The first is, did you see any evidence of hyporheic exchange that was limited by the depth of sediment in the flume? In other words, did you see flow paths that went down and essentially flowed along the bottom of the flume and maybe came back up later?
Yeah, absolutely. So even though we didn't actually model the hyporheic exchange in the flume itself, since I just used the pressure distribution from the flume experiments, what I did was my hyporheic model went about 50 centimeters below, or yeah, 50 centimeters, half a meter below the bed surface. But even though it was only 50 centimeters, I still saw some more regional flow lines that existed within my model. And basically, to describe for everybody else, what that was the hyporheic flow was downwelling, and it was basically tracking along the boundary condition at the bottom of the bed, at the bottom of the model in the subsurface. And then it would eventually, because of my downstream boundary condition, it would upwell back up. But there were a few different flow lines that actually maintained their depth and stayed down there. And those are the roughly 2% of the flow lines that I removed, because to me, those are the more regionalized flow lines that may or may not actually be the hyporheic exchange, but more of the groundwater flow from the river.
Gotcha, cool. And then also, did you do something similar of numerically expanding the experimental domain laterally around the boulders? Because I'm also thinking that you could have like short-circuited flow paths along the walls.
No, that's a great point. And I think that's another limitation of the study, is the fact that even though the walls of the groundwater model itself extended more than half a boulder diameter in the cross-seam direction, I think if you do include a greater area outside of those boulders, then you would probably see more flow lines that are moving laterally around the boulders rather than being forced downstream, because I think that those walls were part of the reason that I was seeing some of the downwelling immediately near the boulders. Another thing worth noting is I did also see, if you were to look at the flow lines in a plan view looking down, the boulders themselves had an effect such that the flow lines were actually kind of following a slalom shape. The imposed conditions from the boulders on the subsurface forced the subsurface, the hyporheic exchange flow, to kind of follow in between the boulders. So that's another kind of important and cool observation that I made. But yes,
the follow-on downstream effects. That's really cool.
Yeah.
So my last question was, given that this was a modeling study, what would be like if you could go back and make measurements in the flume at the time of the experimental runs, what would you say would be your highest priority physical measurements to make?
What I want to do is validate the pressure observations. Since the pressure was indirectly observed through a series of calculations from the surface flow modeling, I'd want to verify the pressure values on the surface of the bed to make sure that they are what are being calculated, and also probably nest some sort of piezometers in the bed to determine kind of what that overall gradient was in the subsurface.
Super. Great. Well, thanks for the presentation. Nice job.
Thanks, Tyler.
Any other question from the public? Meanwhile, the committee member will ask questions later in the second portion of today, basically exam, where will be a closed door, just Taylor and the committee. So we have still a little bit of time for the public to ask questions. If there aren't other questions from the public, so what I would like to suggest is at this point to give a round of applause to Taylor for his presentation. Very, very nice. So we can unmute.
Thanks, everybody.
And then if the rest of the public would leave this the Zoom meeting, and only the committee member will remain on, and then we can start. Probably let's give a 5 minutes break to refresh a little bit, and then 5 minutes, we can start the second portion of the day.
Thank you.
Thanks, everybody. Well
Thank
done.
you, everybody, to join us.
I'm talking to Haley.
Oh, okay. Nice job, Taylor.
Thanks. I felt like I was rambling, but
No, you did a great job.
there's so much to say, and I definitely didn't talk for the length of time that I expected to.
Yeah, it's hard to calibrate that. You never know how you're going to actually perform when you're doing it for real.
Yeah. Jeff, did I hear a cat in there once or twice?
Yeah. My desk is in their pathway. They've got a room outside the house that I built for them, and they run right across my desk.
He's like Lauren, Stephen. The cats are always involved with me.
That's funny. Yeah, we all, do you still feel like an intruder in your own home? That's how I felt for a while when I first started working from home, and my wife and son were here and just like, what's this guy doing here all day?
It wasn't really a foreign thing for us since we basically moved into the house during some sort of quarantine. So
Yeah, that's true.
making our kitchen / dining room the office was.
Oh, okay.
But we do have a little den that will eventually be the office whenever all of this is no longer.
Yeah. So is Haley working in the same? You guys will both work at the table together?
Yeah, we sit right across each other most of the time.
Yeah.
Whenever we have dual meetings going on at the same time, we have to get creative. So I'll go in the bedroom or she'll go in the bedroom.
Yeah.
I'll go outside.
There's definitely such thing as too much together time with your spouse, but you guys have only been together a few years, so yeah, probably haven't hit that yet.
Wait till you've been together 40 years. That will become important to you.
Well, I don't think we'll be in the same house at that point in time, so maybe we'll have our own spaces somewhat by that time.
How many bedrooms do you have in your house?
It's 2-bedroom and then a den.
Oh, okay.
1,500 square feet, but
That's pretty good.
yeah, it's good. It's a good starter home for sure.
Mm-hmm.
Yeah, and equity in the homes are going way up, so that's a plus.
Yeah. That's funny to hear you say that. 6 months ago, you would you had a totally different tune.
I'm just glad we're not playing the game of buying a house still. That was rough.
Yeah.
Angel, you haven't met Angel, Stephen, but he lived in Chile for the last how long has he been there? 3 years, Jeff?
Yeah.
Something like that.
3 or 4 years, yeah.
And he just moved back a few days ago.
Okay. Well.
I don't know if is he renting or did he purchase a house or?
Renting.
Gotcha.
Yeah.
So the other thing that we will need to do, Taylor, before we start is I know that you are recording the seminar, which is very good, but the public part is fine. And now the second part, we should not record the remaining part of the exam.